Probability is an important concept we need to understand as a prerequisite to many of the models we are going to learn in the future. Life is full of uncertainty, and in the business world we can represent these uncertainties with probabilities. Probability is a numerical statement about the likelihood that an event will occur. There are several types of probability we will discuss. The first is called classical probability, also called objective probability. This form of probability is based on the relative frequency of occurrence. To find the probability of an event, we take the number of occurrences of that event divided by the total number of outcomes. One example is the flip of a coin. The probability of flipping heads is 1, as there is only one way to get heads on a coin, divided by 2 because there are two possible outcomes, heads or tails. We can look at another example with a deck of cards. There are 13 spades in a deck of cards, and there are a total of 52 cards or possible outcomes. The approach to probability is called subjective probability. Subjective probability is based on expert opinion, experience, or judgment, and is more of a qualitative approach. This approach is usually used when we do not have historical data or numerical data to use objective probability. We'll talk more about this in a few weeks when we discuss forecasting. Two events are mutually exclusive if only one event can occur for any one trial. For example, on one coin toss you can only have a head or a tail. Think of this as the probability of a head or the probability of a tail. Similarly, on a single dice roll only one number can be displayed, a 1 or a 2 or a 3 or a 4 or a 5 or a 6. Diagrams to express a mutually exclusive event. The Venn diagram on the left shows that the probability of A and B do not touch or intersect. However, the Venn diagram on the right shows the probability of A and B intersecting, and thus they are not mutually exclusive. The next probability concept that you will need to know is about unions and intersections. Let's look at intersections first. Think of an intersection as the probability of A and B. Keyword here is AND. The symbol for an intersection looks like a lowercase n. To find the intersection, we multiply the probabilities together. A union is the set of all outcomes of either of the events. So we are interested in the probability of A or B. The symbol for a union looks like a lowercase u. At a deck of cards and decide we want the probability of the intersection of the number 7 and a heart. We have only one possible outcome out of 52 total outcomes. However, if we want the probability of the union of the numbers 7 and a heart, then we have 16 possible outcomes. There are 13 hearts in a deck of cards and 4 7 cards, with one card being the 7 of hearts. So we subtract 1 from our total possible outcomes, which gives us 16 out of total 52 possible outcomes. We can calculate the union of two events with the additive rule. A union is the probability of A or B. If we find the probability of A and the probability of B and then sum them together, we have the full set of outcomes. Then we need to subtract out the overlap of the probabilities. We can do this by subtracting the intersection of probability A and probability B. The notation we need is the vertical bar. This is read as the probability of A given B. With conditional probability, we are interested in a probability that an event occurs given a condition has already been met. To find this, we take the probability of A times B divided by the probability of B. Independence in probability occurs when two events have no bearing on each other. In this example, whatever the first toss of a coin, it will not affect the second toss of that coin. When this occurs, we can see that the probability of A given B is the same as just the probability of A. If we want to find the probability of a series of events, then we can multiply the probabilities. The probability of A then B, which is a head on the first toss and a head on the second toss, we multiply the probability of A, which is 0.5, and the probability of B, which is also 0.5, we can get the probability of A then B as 0.25, or 25%. Let's look at another example. If we have a bucket of 10 golf balls that includes 3 black balls and 7 green balls, what is the probability of drawing a black ball? Well, we have 3 out of 10 black balls, so our probability is 3 divided by 10, or 0.3, or a 30% chance. If we want to look at the probability on a series of draws, we can calculate that too. What is the probability of drawing 2 green balls in a row? To draw 1 green ball is 7 out of 10, or 0.7, or 70% chance. Then we put the ball back in the bucket and draw again. We have the same odds as the first green ball we pulled at 0.7. We multiply these probabilities together to get 0.49, or a 49% chance we will draw 2 green balls in a row with replacement. Events affect our probabilities due to overlap. With this set of balls, we have some white balls with numbers and some with letters. If we are interested in the probability of white balls, then we must add the probabilities of both kinds of white balls. Let's think of this example for a moment. We have 10 total balls, of those of which 4 are yellow, 3 of which are also lettered. 3 of the balls are numbered. If we select a ball at random, what is the probability of selecting a ball that is neither yellow or numbered? To find this, we can add the probability of a yellow ball, 0.4, plus the probability of a numbered ball, and subtract the overlap of the probability of a yellow numbered ball. This gives us a probability of 0.4, or 40%. Bayes' theorem is the entire reason we are covering probability. In future chapters, we will be using probabilities to make decisions. However, where did those probabilities come from? For the most part, we are arbitrarily selecting probabilities to give our model a start. Maybe we have some expert opinion on how to start with, or which probabilities to start with. After we start analyzing our model, we may find that these probabilities need to be adjusted. We can do this with Bayes' theorem. We call our new revised probabilities posterior probabilities. Think of post, like in post game. Let's do an example. Say you own a casino. You are trying to determine if someone is using a loaded die, or cheating using die that are favorable to the player. You notice a player is able to roll threes in an uncanny way. So you take the dice from him and decide to roll one to see what you get. What is the likelihood that you rolled with the fair die or the loaded die? We know that we have 2 total dice, 1 each of fair and loaded dice. There is a 1 out of 2 possibility, or 0.5 or 50% chance for either of the dice. We also know that the probability of 3 on the fair die was 0.166, or 1 out of 6. The loaded die has a very high likelihood of 3 with a 0.6 probability. The probability of 3 in fair is multiplied, or we have 0.083 chance that both these events have occurred. The probability that the loaded die rolled a 3 is 0.3. Add the 2 probabilities, we get the unconditional probability of rolling a 3 on either die as 0.383. Now we can revise our probabilities by dividing our original probabilities by the probability of rolling a 3 that we obtained with this new information. These are our posterior probabilities for the original problem. The formula for Bayes' theorem is the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B given A times the probability of A plus the probability of B given the complement of A times the probability of the complement of A. The complement of a probability is basically the other side of a probability. The probability of A is 0.3, and the complement of the event of A is 1 minus 0.3, which equals 0.7. To use Bayes' theorem as a more streamlined way to calculate the example we did earlier. Basically, you can plug in all of the numbers instead of having to calculate them out. And we still get our 0.383 in the last part of the equation.